Okay, I'm going to continue the calculations from the previous video. I'm going to use Excel because we'll have to do many calculations to reach equilibrium. And so what I've done is I've set up a spreadsheet here and I create some things that we can consider constant, like the depth of the water layer that's on the surface of the Earth. If we're considering the Earth, the radius of the Earth will be constant. And so we can use those then to calculate the water volume. So if you remember, the water volume is the surface area of the Earth. So 4 times pi, and in Excel you can type pi, open and close parentheses, to get the value of pi to many decimals. I'm going to multiply that by the radius squared, and then I'm going to multiply that by the depth of the water. And the nice thing here is that I can adjust, once I have everything working, I can adjust the depth and see how that affects the equilibrium temperature of the planet just by changing the water depth there. It will change everything in my calculations later. The next thing I need to do is calculate the mass of the water because we're going to use that heat equation for the water warming up. And so the mass is 1,000 kilograms for every meter cubed. So I just need to multiply 1,000 times the volume of the water in meters cubed. And that will give me this number we saw before, 1 times 10 to the 21. And this is the solar constant. So we could conceivably change the radius of the planet and the solar constant to model different planets like Venus or Mars. And then the next constant that I'm going to set is the change in time. So how often are we going to recalculate the temperature in order to try and find out how we get to equilibrium? That'll become a little clearer in just a second. So we need to calculate the input power from the sun. That was equal to the area of a circle, so pi times the radius of the Earth squared. Now, I'm going to calculate this going downward here, and if I try and leave that as just calling on B2, where the radius is, when I pull that formula downward, it's going to try and make that call follow downward with it. In order to keep that from happening, I'm going to put $B, $2. That will hold that fixed on that radius value. So I have pi r squared times the solar constant, and I also need to fix that with the $sign. So I'll put $B, $5. And we get the 1.73 times 10 to the 17. Excel just uses an E to signify 10 raised to them. And so we saw that number before in the hand calculations. The output power coming from the black body radiation, remember that's the surface area of the Earth, which is 4 pi r squared, $signs again, times the efficiency we'll assume is 1, times the physical constant 5.67 raised to the -8, times the temperature raised to the 4th. So I'll click on the temperature and I'm going to raise that to the 4th power. And I don't have anything in here. I'm going to put a 0 for the beginning temperature because we're going to look at how the temperature of the planet warms up. The next thing, I'm going to calculate the net power. That's just equal to the input minus the output radiation. Then I'm going to calculate the energy, so that's the power net times a change in time. So I'll say equals, click on the net power, and then multiply that by the change in time. But that change in time is in a fixed cell. So I'm going to put $signs there. And so we get this 5.47. When we did the hand calculations, it had gotten rounded down to 5.46. So we're going to see a slight difference in the numbers here just because of rounding errors that I did in the hand calculations. So this now is an energy input, and at the beginning there's no time, so there won't be any change in temperature. We can just ignore this cell here because we're at time 0. After 1 year, there will be one of these delta T's. And so I can calculate the change in temperature after 1 year. This is sort of the tricky part of doing these calculations. This change in temperature is going to come from this power that was put into the planet. This net input power warmed the planet, but it didn't happen here in 0. It happened after 1 year. So I'm going to calculate the change in temperature here by typing equals the net power times time divided by the mass of the water, and I'll have to use dollar signs again because I'm going to copy this formula downward, and I'm going to multiply that by the heat capacity of the water, 4184, but all of this needs to be in the denominator under P net times delta T, so I'm going to put parentheses around it. And I see 1.28, that's a little bit smaller than the 1.31 that we calculated by hand, but that came from rounding errors. So what I can do next is these formulas, I can copy them downward by just getting that plus sign at the bottom right corner, drag that downward. What I need to do over here is take the previous temperature and add it to the change in temperature to get what the current temperature would be after 1 year. So I'll type equals, click on the previous temperature, add the change in temperature to get that. And when I do that, it updates. So let me just get rid of that for a second. I don't have any output power here because it's looking at the temperature over here to say how much black body radiation there is. And so it's not until I enter a temperature here, I then will get some output power here. That's going to have an effect here. You don't see it because this number is much smaller than this one, but it's going to have an effect on the net power because these are subtracting from one another. And so the net power is going to decrease as the temperature of the planet warms. And so we're going to see smaller and smaller changes in temperature. But at this point, all of these are properly calling other cells in Excel. And so I can just click and drag them down. And you see the change in temperature is, it appears fairly constant. The temperature is rising here from 0, we're up to 18 Kelvin. We'll keep going 1 year at a time, and I'm going to go all the way out to 200 years. And you can see that the temperature now is somewhere in the 220s. So what I'm going to do is just take a look at how this looks. I'm going to highlight the temperature column and the time column by holding down the control key at the same time as I highlight. And then let me scroll back up to the top, click on Insert, add a scatter graph. And what I see here is that the temperature is still increasing. So what I'm going to do is add more of these so that I go out to, I don't know, let's say 250. Oops. And then I need to update the graph. So I click on the graph, scroll down and see, okay, it ended there. I'm going to just point to the bottom right and drag this down. And then do the same for my X values. And see what happens to the graph. Okay, so we see it's starting to flatten here, so I'm going to keep going. So I want to get it, equilibrium is when the temperature stops changing because the input power and the output power have come into balance with one another. So I'll go out to, what is that, 300? And then add that to the graph. And let's see where we are. Yeah, so we're starting to flatten out. I'm going to go another 50 years just to see what happens. Excel is pretty smart. It recognizes that I'm trying to continue calculations. Okay, there's 350. And so I need to add those to the graph. And now we're really starting to see it flatten out, and the temperature where it's flattening somewhere in the neighborhood of 274. I'm going to show you one other thing that you can do. You can change the interval of time here. So, for example, if I wanted to make this, instead of 1 year, I could type equals 5 times that number of seconds to make it 5 years. Something we have to keep in mind, though, is that that's going to change this because our interval now is 5. So I'd have to say 5, 10, etc. And if I do that, so let me back up. I just pointed here to the bottom right again and double clicked, and it recognized how many elements are on the right of it so that it knew how far to continue that. And now you can see very much an equilibrium happening here, that the temperature stops changing. And I'm going to remove some of the points from the graph just so that we can see a little easier what's going on. I'm going to go back to, let's say, let's go to 450. I think that'll be fine. Okay. And so if we make the time interval a little bit longer, then it takes less points of calculation. But we can see that this is flattening out here at the top. And if we scroll down, we see that the temperature is somewhere in the neighborhood of 277, 278 Kelvin. That would be 0 Celsius or freezing is 273 Kelvin, so we're talking about a few degrees in Celsius above freezing, about 5 degrees Celsius. That would correspond to something like maybe 40 degrees Fahrenheit. So we're getting closer to a model that is giving us the temperature of the Earth. It's not quite right, but I'll give you an extra credit assignment where you can play with some of these parameters to see if you can get it closer. And in another video, I'm going to show how we can make the model a little more complicated, including greenhouse gas effects, in order to get the temperature just a bit warmer and closer to what we actually observe on the Earth.